Today, we would like to thank and acknowledge our sponsors, DC3 Dreams and Boyce Astro. DC3 Dreams provides high-end observatory automation and web-based multi-user remote imaging. The AAVSO Net Observatories use DC3 Dreams ACP Expert for the Bright Star monitors and other programs. The AAVSO Photometric All Sky Survey project, also known as APAS, has used ACP Expert's AI scheduler to automatically acquire over 500,000 star fields, hands off, at a rate of 1,000 square degrees per night. This has resulted in photometry for over 128 million objects in about 99% of the sky. The Boyce Research Initiative and Education Foundation provides online astronomy education, observatory resources, and research experiences to students, student teams, and schools in order to learn how to perform observations, conduct research, and publish their results in scientific journals, such as the Journal of the AAVSO. Please do check out their webpage to learn more about their work. Okay, it is the moment you have all been waiting for. Our first of today's speakers is a very special guest. An astronomy professor at the University of Washington, she has become famous for her work on massive stars, particularly red supergiants, and how they live, evolve, and die. Her list of accomplishments is a mile long. She has observed for over 50 nights on the planet's largest telescopes. She was awarded the 2014 Annie Jump Cannon Award and the 2020 Newton Lace Pierce Prize. And she's even flown over the Antarctic stratosphere in pursuit of her research. On top of all of that, she is a successful author and teacher. She recently published her first popular science book, The Last Stargazers, and her technical book, Astrophysics of Red Supergiants, is one of my favorite astronomy books ever. Between her research and her incredible teaching skill, she's one of my personal heroes, and I do not say that lightly. So, ladies and gentlemen, you can imagine that it is with the utmost excitement that I get to introduce to you today, Dr. Emily Levesque. Dr. Levesque?
Thank you so much for inviting me. I'm so excited to get the chance to speak to everyone today. I'm so glad that you're so excited about my Red Supergiant book. It was the first book I ever wrote and is a personal favorite of mine. And as I share my screen and get us started, that book actually drives a lot of what I'll be talking about today, because red supergiants are one of my primary research focuses. And what I'll be talking about today is red supergiants in general, but framed around a very particular red supergiant and a favorite of mine. So what I'll be talking about today is Betelgeuse, and I'll be arguing that Betelgeuse is pretty cool, which I don't think is a hard argument to make to this crowd, in that it is one, a very cold star, and two, a fascinating one that can, by studying it, sort of highlight a lot of the questions that we have about red supergiants as a whole. So the picture that I have on the screen right now is a gorgeous amateur astrophotograph of the constellation Orion, and you can see Betelgeuse hanging out in Orion's shoulder. And Betelgeuse has fascinated astronomers for decades, but it especially caught everybody's attention beginning late in 2019, because starting around October, November of that year, Betelgeuse started to do this. So you can see that Betelgeuse faded to get dramatically dimmer than we had previously thought than it had ever been before. It was actually at some point the third dimmest star in Orion, transitioning from being the brightest star in Orion. And I love this animation as a way of sort of illustrating what happened, but when it comes to showing great data on how Betelgeuse's brightness has changed with times, you really cannot do better than AAVSO. So we can watch what Betelgeuse has been doing for really years and years as we monitor its brightness. And Betelgeuse has been known to vary a bit. You can see it brightening and dimming and brightening and dimming, but in late 2019, its brightness absolutely plummeted to a degree that had not previously ever been observed in its light curve. And this started to catch astronomers' attention. And the excitement about this really started to come to a head in December of 2019, when Ed Guinan and a couple of his collaborators published an astronomer's telegram describing what they called the fainting of our nearby red supergiant Betelgeuse. And as they described, it was getting unprecedentedly dim. We know that Betelgeuse is a star nearing the end of its life. We know it's an interesting star to watch, So they essentially pointed this out to the community saying, we should really keep an eye on Betelgeuse. The media then found this because this got posted on the internet, and they had the usual calm, measured response that the science media tends to always have to these sorts of stories. There was a flood of articles and headlines going, is Betelgeuse going to explode? Has it already exploded? What is it doing? Surely this is an incredibly exciting event. And watching Betelgeuse dim and then trying to explain why it dimmed was most definitely exciting, but maybe not quite in the way reporters thought. Myself and a lot of other experts on red supergiants spoke to the media when all of this excitement kicked off, and people just kept asking, well, what's happening? What is happening to Betelgeuse? What is Betelgeuse doing? What do we have in store? And our overarching answer over and over when we answered this question was, Betelgeuse, despite the great dimming, as it was dubbed in the media, is not about to die. Probably. And we will come back to this word because the probably that a lot of us tacked onto that answer was really not us being cute and sort of trying to string along media interest. It was an honest answer to our understanding of what Betelgeuse was doing. We didn't think it was about to die, but we couldn't be entirely sure. And I'll get again to why we're not quite sure at the end. But first, it's good to provide some context for what Betelgeuse is and why we're so interested in it. So to do this, I want to take us to the Hertzsprung-Russell diagram, where we can plot pretty much every normal star that we observe. If you plot the star's temperature on the x-axis and you go from really hot on the left to really cold on the right, and if you plot its luminosity on the y-axis, so stars getting brighter as you go up, most normal stars fall into this rough pattern. You can see the vast majority of stars lying along this diagonal that we know as the main sequence, and then you can see lower mass giants and high mass supergiants higher and higher on the plot. Betelgeuse is going to be one of these stars on the upper right, so a red supergiant. This is a very massive star, at least 8 to 10 times the mass of our sun, that has progressed to a late stage of its evolution. It switched from fusing hydrogen in its core to fusing helium in its core, and it's getting ready to end its life. Now, it might end its life as a supernova. It might evolve back into a blue star before that happens. It depends on the star and its mass, but we know that Betelgeuse is starting to reach the end of its life. So this was a great part of what sparked everybody's enthusiasm about Betelgeuse and what prompted us to try and get as close a look as possible at what this star was doing during that great dimming. I think the best picture of the great dimming and what actually happened comes from Miguel Montarget and a research project that he and his group had been doing for months before the great dimming started. They used the very large telescopes in Chile to image Betelgeuse and actually look at a spatially resolved picture of this star's surface. And you can see they got this beautiful little disk of Betelgeuse in January of 2019. They had been observing the star over and over for months and captured it again in December of 2019 after the dimming had started. And you can see the dramatic difference. Betelgeuse went from this to this. It's dramatically dimmer. You can see that it's much dimmer, specifically in the southern hemisphere. It almost looks like the star has changed shape, or that the appearance of a surface has fundamentally evolved over the course of this really amazingly short period of time. So this gave us a look at what the great dimming actually was. We were clearly losing light from this star, and that loss was happening preferentially in the southern hemisphere. So this is where Betelgeuse was at in December of 2019. And then as we kept watching and as beautiful AAVSO data showed us, Betelgeuse recovered. It brightened right back up in around March-ish of 2020. Something was getting better in March of 2020. And then Betelgeuse proceeded to basically behave normally. So this left us puzzling over what had happened and what could possibly have explained this behavior. And a few competing ideas immediately popped up to explain Betelgeuse's really weird appearance and what it might have been. One idea was that that cold or that dark spot that we saw in the southern hemisphere of the star could be explained by a cold patch on the star's surface from convection in the star's outer layers. Another idea was to say maybe this really actually wasn't that weird. We knew Betelgeuse had varied before. We know other red supergiants are very variable. Maybe this was just normal red supergiant variability, and Betelgeuse was doing something not all that different than what it and its fellow red supergiants had done in the past. And then a third idea was that maybe that dark spot in the southern hemisphere of the star came from mass loss, came from the star producing some dust that then sat in front of the star and blocked our view. It would similarly give us that very dark view, but the mechanism behind it would be really different. So these three competing ideas were the three hypotheses that we were trying to test. And as we looked at these questions with respect to Betelgeuse, we really started realizing that these were questions that we had to answer about red supergiants as a whole. It really revealed how much we don't know about stars like this. When it comes to the cold spot from convection, we want to understand the temperatures of red supergiants as a group, and we want to understand what convection in their atmospheres could mean for how these stars look. When it comes to normal red supergiant variability, we really need to understand what normal means. These stars pulsate, they exist in binaries or in groups, they rotate. There's all these different physical things happening to these stars that can contribute to what we see as their variability. And then finally, we don't understand a lot about how red supergiants shed mass and how that mass then condenses into dust, how it contributes to interstellar enrichment, how it winds up impacting our view of red supergiants. So there's a lot we still had to learn about mass loss and dust production before we could think about how that might explain what Betelgeuse had done. So these three questions and these three hypotheses for Betelgeuse are what I'm going to cover in the bulk of my talk. And we'll start by looking at this idea that the dimming came from a cold patch on Betelgeuse's surface caused by convection. So when I talk about convection in these stars, I want to give you an animation showing the scale of what's happening. This is how we've modeled convection on the surface of a red supergiant. It makes the star look like this big, boiling, almost amoeba-like object because the atmospheres of these stars are so huge and cold and puffy. They extend so far out from the star that you wind up getting these huge churning, boiling cells. Now, we see cells like this in stars like our sun, but they're relatively small. In a star like Betelgeuse, you really get variations on these enormous scales. They're comparable to the size of the star itself. So looking at this, you can see how a patch of the star will look pretty bright and then pretty dim as it churns up hot gas from inside the star, and as that gas then cools and falls back deeper into the star's surface. This is most definitely a scenario that could explain weird behavior in hot and cold or bright and dim patches on a red supergiant surface. And we have actually seen this in Betelgeuse itself. This is a resolved image of the disk of Betelgeuse taken back in 2010. And you can see hot patches, medium patches, and cold patches that are similar in scale to that model that I just showed you. So we know that these sorts of churning things can really impact what Betelgeuse's surface is going to look like. So could that explain what we saw as we go from January of 2019 to December of 2019? Could that dim southern hemisphere just be a big cold spot dragged to the surface that's changing how Betelgeuse looks? This was the hypothesis that my colleagues and I actually decided to test while Betelgeuse was going through its great dimming. It had been getting dimmer and dimmer. It reached a sort of brightness minimum in February of 2020. And around when that happened, we started thinking, we're just too curious. We really think this could come from the star cooling off. We want to measure Betelgeuse's temperature right now and see if it's noticeably colder than it was before. So to show you how we measure the temperature of a star like this, I want to show this example of a spectrum of a red supergiant. So right now we're looking at a model or simulated spectrum of what light would look like from a red supergiant in a simulated star if you were to observe all that light and then just sort it out by wavelength. So you put the bluest light on the left and the reddest light on the right, and then look at how bright the star is at sort of every individual color along the way. Now you can see just looking at the shape of the line plotted here that you're getting more red light than blue light. It makes sense for a red supergiant. If you look at how this spectrum changes, how this light changes as we cool off our model star, you'll see some telltale signs of how we can measure one of these stars' temperatures really well. Right now, we're looking at the spectrum of a red supergiant that's about 4,000 Kelvin at its surface. If we gave it a spectral type, its spectral type would be a K1. Now let's watch how this changes as we animate it and cool the star off from 4,000 Kelvin down to 3,400 Kelvin. Now you can see the really dramatic difference. The star gets redder. You can see how much we lose blue light. And you also see these sort of big bites taken out of the spectrum. Those big features are absorption bands from titanium oxide molecules. These stars are actually so cold that as they get cooler and cooler, we're able to build up molecules in the atmosphere. And as we get more and more of those molecules, they absorb more and more light, and we get these big telltale dips in the spectrum that get stronger as the star gets colder. So what we could do with something like Betelgeuse is compare a spectrum taken when Betelgeuse was nice and bright and normal looking to a spectrum taken when Betelgeuse was very dim, and see if this was explained by the star being much colder and those titanium oxide bands being much bigger. So we happen to have a spectrum of Betelgeuse from 2004 when it was a pretty normal, typical brightness. We then went and observed a second spectrum of Betelgeuse in February of 2020. Now, in 2004, this spectrum corresponded to a temperature of about 3,650 Kelvin. When we re-observed the star in the middle of the Great Dimming in 2020, we got this. So you can tell that the spectrum is a lot dimmer in 2020 than it was in 2004. It simply isn't emitting as much flux. But when we measured the temperature, we didn't see a huge difference. In 2020, Betelgeuse had a surface temperature of about 3,600 Kelvin as compared to 3,650. And our error bars on these temperature measurements are plus or minus 25 Kelvin. So we were really barely seeing a difference at all. You can see just how similar the lines are if we do a different version of this plot and stack the 2004 spectrum in dashed red line and the 2020 spectrum in a solid black line. The depths of those little titanium oxide bands are almost exactly the same. The star had maybe cooled off a little by about 50 Kelvin, but that wasn't nearly enough to explain the incredibly dramatic drop in the star's magnitude that we saw from our observations. So based on our observations, we concluded that temperature, or at least temperature by itself, couldn't explain Betelgeuse's dimming. So we probably weren't seeing the effects of a cold spot on the star's surface produced by a convected atmosphere. So this then brings us to the second idea. Maybe what we're seeing, again, isn't that weird? Maybe we're seeing normal variability from red supergiants, and Betelgeuse is just doing what you would expect a red supergiant to do. Now, this means that we need to think about the different things that could cause either regular or random irregular variations in the brightness of a red supergiant. And if you think about this and try to list off, oh, maybe the star was dusty, maybe the star was pulsating, or maybe there was convection going on, maybe there's a companion, you can throw out heaps and heaps of ideas for what could cause strange variations in the brightness of one of these stars. And I'll look at a few of these different explanations in a little more detail. First, we know that red supergiants and cold stars like this pulsate. Their atmospheres effectively shrink and grow at different cadences and for different reasons. Regular red supergiants undergo all sorts of weird variations. This is a sample of light curves from just 3 different fairly typical red supergiants in a nearby galaxy. And if I hadn't told you, you probably wouldn't guess that these were 3 of the same type of star. Their light curves look so different. Some of them really show nice regular-ish variations like the one on the bottom. Some have very long-term variations that change over the course of years, like the one in the middle. And other ones, like the one on top, are just random. There's irregular changes in their brightness, and we can't put our finger on exactly why. We know that at least some of these come from those pulsations that I mentioned, so the atmosphere of the star shrinking and growing. And interestingly, Betelgeuse is an example of a red supergiant where we think we do see pulsation behavior. If we bring up the beautiful AAVSO data again and look at the light curve of Betelgeuse, you could kind of pick out a period of sorts. You could look at the brightening and dimming pattern and say, well, there's a period of about 430 days. Based on what we know about Betelgeuse, we think that that could be coming from the star's pulsations as it shrinks and then grows and sort of puffs off a little bit of atmosphere and then collapses back a bit. So it doesn't look like the timing of the Great Dimming is that weird. It actually lands right when we would have expected a local minimum in Betelgeuse's light curve. But that explains when the Great Dimming happened. It doesn't explain why it was so great. We would have expected just a normal dip in Betelgeuse's light curve, not this record-settingly low brightness. So pulsations don't explain the extremity of the Great Dimming. It at most suggests that pulsations in Betelgeuse's atmosphere contributed to whatever we saw. So what else could cause variations in these stars' brightness? Another possibility that astronomers are paying more and more attention to these days is binary interaction. What if a red supergiant or a star like Betelgeuse is in a binary? Wouldn't you expect to see variations in the star's brightness based on how the stars interact? So this gets to a really challenging question about red supergiants, and one that a recently graduated PhD student in my group, Catherine Nugent, has been focusing on in her research. We know that binaries should impact how bright red supergiants look, which means that we really should understand just how many red supergiants are in binaries. How many of these have binary companions at all? How many have binary companions that might block their light or interact with them or somehow change how they look? Even identifying binary red supergiants is challenging. I'm sure a lot of folks on this webinar right now who are used to observing variable stars have gotten used to the idea of identifying binaries based on eclipses or other things that you can pick out in a star's light curve. You monitor a star's brightness, and if it brightens and dims very regularly, that's a great sign that there might be a binary companion. In red supergiants, this doesn't work as well, because we know that just convection alone can absolutely wreak havoc on the star's light curve. The light curves are so messy and have so many different things contributing to their brightness that identifying a binary just based on brightness changes is pretty much a non-starter. We've tried, and even using machine learning, we can't really disentangle all the different things that contribute to a red supergiant's brightness. What we can do is look at the star's spectrum again. So this is very similar to what I showed you before. It's the spectrum of a red supergiant sorted out from bluest light to reddest light. And if you were to glance at this particular plot, it looks just like the plot I showed you before. It kind of looks like the spectrum of Betelgeuse. It seems to show a normal red supergiant. The star is brightest where the light is kind of red, and you can see those big broad bands of absorption from titanium oxide molecules. But if you were to zoom in on the very bluest part of this star's spectrum and take a very close look, you'd see these extra little dips in the spectrum. So light being absorbed by very specific atoms. In this case, those are all signs of absorption by hydrogen atoms. You wouldn't expect to see something like this in the blue spectrum of a regular red supergiant, but you do see this in a red supergiant that has a B star for a companion. B star spectra look exactly like this. And in this part of the red supergiant spectrum, the red star is actually so dim that we can see the B star binary companion dominating the light. So when Catherine discovered this, this became a wonderful signature for how to find red supergiants with stellar companions. This was one of our first examples. We'd really only found a dozen before Catherine's work of red supergiants with B star binary companions. Now that Catherine's finished her research on this, the number of known binary red supergiants has increased by an order of magnitude. We've gone from dozens to hundreds and hundreds. And the types of spectra look really different. If you look at these three examples at the bottom of the screen, they really start to stand out as odd types of red supergiants or odd types of stars. So Catherine got amazing at finding stars like this. she actually was able to calculate the red supergiant binary fraction as somewhere between 15 and 40%. So between 15 and 40% of red supergiants have these binary companions that could potentially impact their brightness and how their brightness evolves. I know that number 15 to 40% actually sounds really broad, but there's a reason. The binary fraction of red supergiants actually changes depending on where those red supergiants are born. Red supergiants in the Milky Way probably have a pretty high fraction of binary companions. Red supergiants in other galaxies, like the Milky Way's little satellites, the Large and Small Magellanic Clouds, have a lower binary fraction because the chemistry of those galaxies is more metal depleted. And we think the content of metals in a galaxy seems to make a real difference in how many red supergiants have companions. So it looks like a good number of red supergiants have companions. What does that mean for how they might vary and whether we might see just normal variability in their light curves? This could matter just by virtue of the two stars orbiting one another and contributing different amounts of light to what we observe. Others could matter even more because if a red supergiant interacts with its companion, it actually impacts the star's evolution. You can imagine a binary that looks sort of like the drawing that I have on the right of the screen here, where you have a red supergiant primary star and a little blue secondary star happily orbiting one another, but not really interacting in any way. If we observe the light curve, we just see the effect of the star's orbit. But if that red supergiant gets bigger, and we know red supergiants are enormous, if we dropped one at the center of our solar system, it would reach out to the orbit of Jupiter, possibly even beyond. If we had a really big red supergiant, it could actually overflow the gravitational boundaries of that binary and start to pour mass onto that blue star. It could actually start to lose some of its mass, change how the blue star is evolving. As the blue star gets closer and closer, it could start ripping mass off of the red supergiant. So it winds up making a really big difference in how the red supergiant evolves. If this really gets extreme, that red supergiant could actually reach out and swallow the companion star. The B star is effectively consumed by those big boiling outer layers of the red supergiant, and you'll lead to a merger of a red supergiant with its companion. Now, this is very interesting because we actually think that Betelgeuse might have already undergone a merger. We think that it might have already had a stellar companion that it pretty much already ate. We think this because Betelgeuse is actually spinning a little bit quickly by red supergiant standards. It's spinning at an angular velocity of about 15 kilometers per second. And we think this could be explained by Betelgeuse eating an old companion and sort of picking up that star's angular momentum as it spins. So we don't necessarily think that this explains Betelgeuse's great dimming, but it's excellent context for how in a star like this, interaction with the binary is going to affect the physical properties of the star and how it evolves. So this kind of merger where a star like Betelgeuse swallows up a little blue companion is already a pretty cool thing that we can imagine happening to a red supergiant. These sorts of binary mergers can actually get even weirder and produce something called a Thorne-Zhitkov object. So I'll take just a momentary aside to talk about what Thorne-Zhitkov objects are. So these are this very weird, currently still theoretical class of star where we imagine a neutron star core surrounded by a big puffy envelope. So put another way, these are stars that look like red supergiants, but instead of cores that are fusing helium into carbon, they have cores supported by quantum degeneracy pressure. They have cores supported by basically being neutron stars. And if you look at how we think these stars form, you can see exactly why this matters when we talk about binary evolution and red supergiants. You can imagine two blue stars sitting in a binary like we're seeing in this animation. These two stars are both blue supergiants. One is going to be the more massive of the two. It will end its life and produce a supernova. Left behind by that supernova will be a neutron star. Now, when that neutron star's companion, which is still a blue supergiant, puffs up and becomes a red supergiant, it swallows that neutron star. The neutron star is actually able to spiral into the core of the red supergiant, disrupt the core and the fusion that's occurring, and then replace it. And we wind up with this very weird thing called the Thornton-Gov object. It's pretty much the most extreme example of a red supergiant binary merger that you can imagine. Amazingly, back in 2014, we discovered what we think is the first Thornton-Gov object candidate. We saw a red supergiant in the Small Magellanic Cloud that had these weird smoking gun chemical anomalies in its atmosphere that we think indicate that it has a neutron star core. So we're now currently searching for more of these. We're curious about things like the systems that make Thornton-Gov objects, because prior to that merger, we think these stars should be red supergiants with neutron star companions. As mass gets dragged from the red supergiant onto the neutron star, that should emit X-rays. So we should see these as what we call high mass X-ray binaries. We want to know if there's other ways we can tell that a star is a Thornton-Gov object. How do we know, for example, that Betelgeuse isn't one, but another red supergiant is? For the most part, it's very hard to tell, but we know that Thornton-Gov objects should be pretty rare, so we're quite certain Betelgeuse isn't one. But when it comes to other stars, we might want to study their light curves and see if there's unusual brightening and dimming periods that we should identify. We recently did some research showing that these stars should actually emit gravitational waves, so we could start looking for them using gravitational wave observatories like LIGO. And we'd like to know if they have observable signatures outside the optical spectrum where we're used to working. If, for example, we could find signs of them in the infrared. We want to know how many Thornton-Gov objects there are and how long they're expected to live. These stars should be fairly rare, but some optimistic estimates suggest that maybe 1 in 100 regular red supergiants could actually be Thornton-Gov objects. So we'd like to know how many are out there for us to look for. And then finally, we want to know how these stars die. Do they leave behind a neutron star after those outer layers of the star have puffed away? Do they die as a supernova of some sort? Does that neutron star collapse directly to a black hole and just swallow the whole red supergiant with it? We really don't know. So all of these are open questions relating to Thornton-Gov objects in particular and binary evolution of red supergiants in general. So when we talk about binaries as they relate to red supergiants, we want to understand how they merge, what those mergers make, how they interact, period, and how those binaries impact their brightness. It's a fascinating topic, and it directly relates to Betelgeuse because, as I said, we think Betelgeuse might have undergone a merger, but binary interaction couldn't explain the weird great dimming of Betelgeuse. We think this is more probably a part of Betelgeuse's history than an explanation of what it's doing now. So we've talked about how pulsations can impact a red supergiant's brightness, and we've talked about how binaries can impact brightness. Another thing on this list is this idea of dust production or mass loss. How could that impact the apparent brightness of a red supergiant? This actually takes us to the last theory explaining Betelgeuse's great dimming. Were we seeing some effect of mass loss or dust production around this star? So we know that red supergiants shed huge quantities of mass from their outer layers during their lifetimes. I mentioned that their atmospheres are big and puffy and cold. And as these stars pulsate, we think that those pulsations could help to puff off gas, and that gas will then condense into dust. We still really do not have a detailed picture of how this mechanism works, but we see huge examples of this around stars like Betelgeuse. If you look at a much wider picture of Betelgeuse and its immediate environment, you see an image like this. Now, this image is actually tailored to observe the dust around Betelgeuse and observe it at the wavelengths where that dust glows. And you can see huge amounts of dust that have been shed by this star and are now drifting out into the interstellar medium and serving potentially to get in our way and mess with our view of Betelgeuse. So we know that shedding this mass can really change the evolution of a red supergiant, and we know that it can change its appearance as a function of wavelength. The really interesting example of this that I want to show you is actually looking first at a wavelength that we haven't talked about before, which is mid-infrared wavelengths much longer than what we're observing from the ground or what we're observing with our eyes. Red supergiants do produce a lot of dust, and we see signs of that dust, but we can tell that their dust is really different than the kind of classical dust made by low mass stars and the dust that hangs out in the interstellar medium. This dust has a very unusual chemistry. It's silicate rich. Normal dust is more carbon rich. You see weird examples of things like amorphous carbons. You see amazing compounds named polycyclic aromatic hydrocarbons. Understandably, we abbreviate this as PAH, but it speaks to the strange chemistry and the strange dust grains produced around stars like this. So the plot that I have on the screen now is a spectrum again, showing the bluest light on the left and the reddest light on the right, but we're comparing the blue dotted line, what we think a regular red supergiant would look like, with actual observations or actual predictions in black and red of a red supergiant with some dust around it. And you can see that as we get to the reddest light, as we really look at very infrared light, you see excess light from the dust. The dust is actually glowing and contributing to the light that we see from the star. Betelgeuse is a great example of this. We know it's pretty dusty. There are actually red supergiants that are even dustier than Betelgeuse, and we can tell because you wind up with even more excess light in the infrared. We know from studying that dust and actually looking at the light emitted by the dust itself that there are really odd chemical anomalies in this dust, and there are really unique signatures of this dust that can help us understand how it was formed, where it came from, and how it might interact with light at other wavelengths. The plot that I'm showing here is actually a plot from SOFIA, which is the Stratospheric Observatory for Infrared Astronomy. It's an infrared telescope operated out the back door of a specially modified Boeing 747. It flies up into the stratosphere, well above most of the water vapor in our atmosphere, so that it can capture these mid-infrared wavelengths that we can't otherwise get from the ground. We've recently conducted a survey of red supergiants using SOFIA to specifically try and get at what this dust is made out of, how it forms, and how it interacts with a red supergiant's sort of circumstellar environment. Looking back in the optical wavelengths where we can study red supergiants from the ground, we also already know that red supergiant dust does something weird to red supergiant light, the kind of light we observe in something like Betelgeuse's great dimming. The dust that red supergiants make is much bigger than the dust formed by other stars. The dust grains are really big compared to the normal dust that you see just in interstellar space. What this means is that the dust behaves in a way that we call gray. Very tiny dust grains will absorb blue light more than red light, and it really winds up skewing the colors of things that we see if we're looking through a huge amount of dust. A red supergiant won't quite behave that way. The dust grains around these stars are so bright that they just sort of preferentially dim all the light the same. In fact, when you try to model the behavior of dust around a red supergiant and compare it to data, if you take data from a red supergiant shown in black and a model of a dusty red supergiant shown in red, if you don't account for that unusual grain size, you wind up with a sort of excess amount of light from the red supergiant in the blue or the near UV. Basically, you're not losing as much dust there as you would, losing as much light there as you would expect due to dust, because the dust is so strange. So the blue light is a little bit brighter than you would expect. This then takes me back to our observations of Betelgeuse during its great dimming in 2020. You can see the 2004 spectrum in red, and you can see the 2020 spectrum in black. We think that this 2020 dimming happened due to dust because the whole red supergiant starts to dim. We actually think we see this excess in the blue coming from the large grain dust that you would specifically expect around a red supergiant like Betelgeuse. So these observations fit with the explanation that we're not seeing Betelgeuse dimming just because it's cold. We're not seeing normal red supergiant variations. We're seeing the effect of a big dust cloud. So we think that from January of 2019 to December of 2019, a huge cloud of dust formed and blocked the light from the southern hemisphere of Betelgeuse, leading to this very dramatic dimming. Now, this was our contribution to a whole bunch of research that was done on Betelgeuse and the Great Dimming. And when we put everybody's research together, it turns out we actually see the combined effects of several different phenomena. And they're the phenomena that I talked about here. All of these explanations actually come into play in explaining what happened to Betelgeuse. We know that the dimming was clearest in the southern hemisphere. We think that we have some evidence that Betelgeuse was a little bit cooler, not enough to explain the dimming on its own, but enough to show that there was a little bit of surface convection going on. We think that that coolness, while not enough to explain the dimming, could have helped produce a huge amount of dust thanks to cooling in the atmosphere, leading to more dust condensing around the star in the southern hemisphere. With this evidence for the big, large grain gray dust blocking light from Betelgeuse, we think that must have come from an earlier mass loss event driven by pulsations. So putting it all together, Betelgeuse was pulsating, shrank a little, puffed off some material. The fact that its surface started to cool off a little bit let that material condense into dust, and that dust then blocked our view and gave us what we saw as the Great Dimming. So all of these pieces have to be put together to give us that ultimate puff of dust that we then saw explaining the Great Dimming. What's really interesting here is that nothing that I've just listed should be special or unique to Betelgeuse. We should see this same behavior happening in other red supergiants. Nothing about this suggests that Betelgeuse is doing something strange. It more looks like we just caught it at an interesting time in its evolution and observed this dimming. So none of this is that alarming. Not that this suggests that something is wrong, and none of this suggests that Betelgeuse is about to die. So despite the Great Dimming, Betelgeuse is not about to die, probably. So I promised at the start of this talk that I would explain that probably. And the reason behind that is that there are several big gaps in our knowledge when it comes to explaining red supergiants and supernovae and how these stars actually die. We have pre-explosion images of a few stars that we know were red supergiants prior to making a supernova, but these images are really limited. They basically count on us being lucky enough to have captured a picture of a red supergiant before it died as a supernova years later. So we get these basically by serendipity, and the images tend to be years old. So we don't know what these stars look like in, say, the days or weeks before they die. We also know, so you can see a red supergiant like that disappearing, but the disappearance was years apart when we go from the pre-image to the post-image. We also know that late time evolution of red supergiants could prove really erratic. If you try to plot how a red supergiant looks as it nears the end of its life on the Hertzsprung-Russell diagram that I showed earlier, where we put temperature on the x-axis and brightness on the y-axis, you can see that something like shedding mass or rotating or not rotating can affect how it looks. If we try to incorporate every single detail of what happens inside a red supergiant and then predict how it's going to look on this plot, it looks like this. This is a real simulation. It's not, a kid scribbling on a wall. This is how chaotic we think these stars' evolution is going to be. So predicting how they're going to look in those final days before they collapse is incredibly difficult. We also really don't know what the spectrum of a red supergiant or any dying star is going to look like right before it dies. The only progenitor spectrum we've ever captured was actually from supernova 1987A. And this is the spectrum of the star that died in that supernova. It was taken 10 years earlier, and it was a very unusual blue supergiant rather than the red supergiants that we're used to capturing prior to a supernova collapsing. So an interesting thing about supernova 1987A that I love bringing up in this talk is that it's not just our only example of a pre-supernova spectrum. It was also, much like Betelgeuse, a naked eye event. It first appeared as this little extra pinpoint of light. It was visible to the naked eye, and it showed up in the large Magellanic Cloud. You can see the little extra bit of light right there. So today, we know supernova 1987A from these classic Hubble images showing these strange triple rings emitted from the supernova, but all of these different observational pieces, so the progenitor spectrum, the naked eye discovery of 87A, and then this great view that we got from Hubble combine to give us the infamous event that we know today. So much like watching Betelgeuse dim, so much so that you could see it with the naked eye, 87A was an event that started as a naked eye event and then turned into this dramatic research subject spanned by so many different telescopes. And this takes me to my final point for this talk. I've shown a lot of data over the course of this talk, and I just wanted to highlight a sample of the many observational tools that contributed to what we've seen. So we've seen data from really big 6 and 8 meter and up telescopes, including those amazing spatially resolved images of the disk of Betelgeuse. We've seen data from telescopes that are amazing for big sky surveys or for capturing the spectroscopy that we needed to explain what Betelgeuse was doing. We used ground-based telescopes. We used space-based telescopes. We split the difference and got some great data from our flying telescope airborne observatory, SOFIA. We see pretty much every wavelength sampled here. It's just a wealth of observational resources, but there's a couple entries on this slide that I want to highlight. And one is the amazing value of amateur data for research like this. So the light curve of Betelgeuse that I kept showing throughout this talk comes from AAVSO data. I'll admit that the picture I'm using here isn't quite of an AAVSO observation, but it was from what I thought was an amazing backyard setup, because that's my dad and I when I was about 8 with our little backyard Celestron. We were just casually stargazing. We weren't gathering data, but even that was amazing. And the value of stargazing and naked eye astronomy is also something that we've seen in this talk. So this last picture is a picture of Oscar de Halde, who works at Las Campanas Observatory as a telescope operator. And he's one of only a handful of people in the history of the planet to discover a supernova with the naked eye. He was the one who discovered supernova 87A. This great dimming of Betelgeuse that I've been covering in this talk is another one of those really rare examples of naked eye stellar astronomy. So something happening to a star in our cosmic backyard on a brightness and on a time scale that we can just see by looking up. So for those of us who use the rest of the telescopes on this list, much of the value of naked eye astronomy is in that spark of curiosity that grabs our attention or that grabs the public's attention, that makes them wonder if a beloved star in their night sky is about to die. So when I wrote my book, The Last Stargazers, I interviewed over 100 astronomers in our community. And so many people told me their sort of origin stories of how they were mesmerized by looking at the stars or by their first view of a dark sky. So my book looks at how astronomy is changing and how the way we do our jobs is changing. But a lot of these changes come back to this amazing suite of tools that you see on the screen now and what the future holds for all of us as scientists and as stargazers. Now, to finally wrap up very quickly, I've talked about what our future holds as stargazers. I want to touch on what Betelgeuse's future holds. I showed you these two spectra earlier of what Betelgeuse looked like in 2004 and 2020. We actually went back and got another spectrum of Betelgeuse earlier this year in 2021, and I'll show that spectrum now in blue. And it seems to be back to normal. The blue spectrum almost perfectly covers the red spectrum from 2004. Betelgeuse has recovered from its dusty incident. It's now back to its normal brightness, and it seems to be behaving very normally. So all of this suggests that Betelgeuse is back to the way it's supposed to look in the sky, and it's not about to die, probably. I think we should all keep an eye on it this winter, just in case. So on that note, I'm happy to leave this up or stop sharing my screen so I can see all of you and answer whatever questions you might have. And thank you again very much for having me.
Thank you so much, Dr. Levesque. That was fantastic. We'll go to some questions now. So first of all, from Joseph Birch, he has asked if you can measure a red supergiant's convection by sort of listening to its sound resonance. So I assume he's talking about astroseismology there.
Oh, that's a great question. So there was another talk given to AAVSO a few months ago by another one of my PhD students who's also now just defended his PhD. His name was Trevor Dorn Wallenstein. I don't know if these talks are archived and you can go back and look at it, but one of his specialties is astroseismology of evolved massive stars. So things like red supergiants or yellow supergiants. Doing astroseismology on these stars is really hard. And it again comes back to that convection, because between their convection and pulsations and mass loss, and in some cases binary companions, it's really hard for us to disentangle what is an astroseismic signature versus what is a dust absorption signature or a different pulsation than the mode that we're trying to detect. Trevor is making, I think, the best inroads in the field now into actually doing astroseismology on stars like this and untangling all that oddity. So it would be amazing if we could use astroseismology to map their convection, or even better, to get at what the cores of these stars are. One of the dreams that we have is doing astroseismology to see if there's really a neutron star buried inside a Thorne-Jitgov object candidate. So it would be an amazing tool to use. It's just computationally really gnarly. So we're still picking apart the bits of it in order to pull out the relevant data.
Great answer, thank you. And yes, Trevor Dorn-Wallenstein's talk was recorded, and it can now be accessed on our YouTube channel, where we have an archive of these webinars.
Excellent.
All right, next question from Yogesh Chavan. Why does titanium oxide around Betelgeuse produce this particular sawtooth shape in its spectrum?
Yeah, it's a really unusual look. I'll back up just so we can look at it again. So understanding the spectral signature of a molecule is nightmarishly hard. I teach a class at the University of Washington on sort of how stars work. I teach it at both the undergraduate and graduate level, and we step through, the math for figuring out how hydrogen absorption looks. And even that, we have to wildly oversimplify it to just imagine one little line of absorption as a little bit of light at a really specific wavelength gets absorbed by a hydrogen atom. To deal with molecules, there are actually people who do laboratory astrophysics and really try to recreate sort of the conditions you would expect in a stellar atmosphere. The sawtooth shape just has to do with the fact that there are such a big mess of transitions possible as electrons jump around these molecules that you wind up with a much messier sort of spectral signature than a nice, neat little line. I know that we can dig into things like why there is, for example, that sharp leading edge and then a zigzag as it goes up, but it all comes back to the molecular structure of titanium oxide. If you look elsewhere in a star's spectrum, you see absorption from vanadium oxide, from sulfur, from silicon oxide, from carbon monoxide, and they tend to have similarly sort of sawtooth-like shapes with subtle differences that I know get back to the molecule structure, but sussing out why is actually a lab astrophysics and more chemistry thing. So we, for the most part, get very carefully computed lists and models of what this should look like. And as they are refined and refined, they start matching observations even better. But it just comes back to the molecular structure.
Thank you. Okay, now we've got several different questions, which are all on the same general topic, which is what the AAVSO should be doing for future observations of Betelgeuse and other red supergiants. So, for instance,
Yes.
Pablo has asked specifically if Betelgeuse is currently being monitored around the clock by observatories around the globe. And either way, should we AAVSO members in the audience start including Betelgeuse in our observing programs?
So I'm sure it's being very carefully monitored, even more so than it was before. Astronomers like Ed Guinan is one great example, has been keeping an eye on Betelgeuse for years. Andrea Dupree has a Hubble Space Telescope observation. So there are heaps of professional resources now being dedicated to Betelgeuse, and absolutely AAVSO should keep studying it, because no matter how much we want to look at stars like this, we never get as much telescope time as we want. Who does? But there's always going to be resources dedicated to Betelgeuse sporadically. But I don't, for example, think that there is a professional observatory getting the brightness of Betelgeuse every single night. It's now included in some big surveys, but ironically, Betelgeuse is too bright to observe with a lot of our big telescopes. When we got our spectrum of Betelgeuse, we got it with the 4.3 meter Lowell Discovery Telescope. And my collaborator did the observations, and he had Betelgeuse half blocked with the dome of the building to acquire it because it was saturating the acquisition camera. And we then put in like the biggest neutral density filter we could find. I remember one of the nights we were desperately hoping for light clouds so that it wouldn't be so bright that it saturated the detector. So we desperately need excellent small telescopes looking at Betelgeuse. Photometry of it is always amazing. The more wavelengths you can get, like if you get blue and B band and V band and R band, like as many different bands as you can get help. Watching how the star's color changes with time is always fascinating. And if anybody's getting spectroscopy and likes doing spectroscopy, get spectra of Betelgeuse as often as you can. If you can flux calibrate it, that's amazing. Even if you can't, just looking at those titanium oxide bands and how they change would be amazing. If I had infinite telescopes at my disposal, I would just be getting spectra of every red supergiant every night to watch how they change.
That's wonderful to hear. That leads me into my next question, actually, which is because I'm in the very early stages of organizing a group of AAVSO members and others to monitor a list of the brightest red supergiants spectroscopically as often as possible. And I was going to ask if that kind of data at resolutions, say, are some people are going to be working at like R400, some people are going to be working at R16,000 and just looking at like hydrogen alpha. Would that kind of varied data set, but covering a lot of stars frequently, would that be of use to you?
Absolutely. So even something like R400 is enough to pick up, like you can get the broad titanium oxide bands in there. You're maybe not going to get little molecular lines, but for something like a red supergiant, we don't need them. And if somebody is doing something at R of 16,000, like a shell level, that I think of that as like borderline a shell resolution. Those are wonderful too. We have some really weird red supergiants that I actually have a new graduate student starting to work on that show emission lines. We think these might have B star companions that are actually accreting sort of shells or disks around them, making them what we call BE stars. And looking at the emission lines, looking at how the emission lines change with time is really interesting. So any spectra are good spectra. I'm a lifelong spectroscopist. It really disappoints reporters when they ask for pictures of my research. And I think they want like a beautiful, picture like this of Betelgeuse. And instead I'm pointing at this going, isn't this awesome? And it doesn't make for, a good Discovery magazine front page, but there's so much information to be pulled from spectroscopy at any wavelength, at any resolution that yes, all of that would be super helpful.
Excellent. Well, great to know. And so last question on the topic. Now you may have kind of just answered this, but let's frame it as prioritization. What kinds of new data would you need to solve the next mystery that you want to work on? Photometry, spectroscopy, which would be more important here?
I always default to spectroscopy.
Yeah,
spectroscopy is just really, really precise photometry, right? It's just photometry at every individual wavelength. But what I'm actually becoming pretty interested in is studying red supergiants in the infrared. We've done a wonderful job of studying stars for decades in the optical regime, but a lot of our next generation resources in astronomy are going to be infrared focused. James Webb is going to be an infrared telescope. Nancy Grace Roman is going to be an infrared telescope. And we are getting ready for this big infrared window onto the universe to open up. And we know way less about these stars in the IR than we do in the optical. One of the things I really want to find is tools that let us translate from one to the other. Looking at the spectra that I have on the screen right now, we can get a temperature out of these stars' optical spectra. We can maybe measure temperatures in the infrared if we find lines that are temperature dependent, but these stars are so complicated that by the time you're looking at infrared light as opposed to optical light, you're actually looking at a different part of the star. You're not looking as deep into the star. And it means that the physical temperature you measure in the IR might not match the temperature in the optical unless you understand them really well and can translate between them. So I'm really trying to get a head start on studying red supergiants in the infrared and comparing the answers we get in the infrared to the answers we get in the optical, so that when James Webb starts observing, hopefully, or when Nancy Grace Roman launches, we'll be able to very quickly start pointing these telescopes, which are perfect for understanding red supergiants, at these samples and translate what we're observing to what we've done before. So anybody that's working, I know amateur infrared is really hard. Like this is really difficult technology, but anybody working in that area in particular, this is a great place to make progress.
Great. Well, thank you. And let's see. Next, we only have time to take like 2 more questions here, so we'll try and hurry. But there's a question from Kate Britton asking if there is a list of red supergiants which have binary companions.
There is. I don't know that you could necessarily look up an archive and find a list, but if you look at papers by Catherine Nugent, so it's Neugent, she has been building a library of red supergiants with B-star companions, which is pretty much the vast majority of what we think red supergiant companions should be. A tiny handful of red supergiants will have more massive companions, but for the most part, they all have B-star companions. She's up to hundreds of these stars, and some of them are in Andromeda or in M33. Some are in the Magellanic Clouds, but I would look at her papers as a starter reference for these. One thing we don't yet know about Catherine's binaries is we don't know how many might be eclipsing or how many might be interacting or not interacting. That's the research she's actually pursuing as a postdoc. But observations of those would be really interesting.
Great, thanks. And all right, our last question here comes from Yogesh Chavan, who has asked if the chemical composition of a star has any effect on its luminosity and lifespan.
Absolutely. So it's a great question. And the chemical composition of a star is one of the primary things driving what happens to it. And this ranges from the composition in the star's core. It tells us how much fuel the star has to fuse, to the chemical composition in its atmosphere, because we think that affects how the star sheds its mass. So you might wind up with, say, a star that has a lot of fresh hydrogen or helium to fuel its core because the star is rotating and getting sort of mixed, and that will help the star live longer. You might have a star that has a lot of metal, and in astronomy, everything that isn't hydrogen or helium is a metal. If any of you are chemists, I'm so sorry. But anything that's a sort of heavier element in a star's atmosphere could contribute to how that star sheds mass, because you actually get photon pressure on those metals as they absorb the star's light that helps drive gas away from the star. So chemical composition is a huge aspect of understanding these stars and how they work.
Very cool. Thank you. Now, unfortunately, that's all the questions that we have time for, although there are still a couple left. If you would like, Dr. Levesque, you can type a written answer to those using the Q&A box at the bottom of your Zoom window. You're not obligated to, but you're welcome to do that if you'd like. All right. So let me go ahead and introduce our next speaker. So our next speaker is a researcher from Poland who actually initially began his career not in astronomy, but in music. It was during his musical studies in Poland that astronomy captured his interest, and so he began to study at the Nicholas Copernicus University, where he used the O-C diagram to research circumbinary exoplanets, which are those which orbit around a binary system instead of a single star. In early 2020, he switched gears and requested help from AAVSO observers to monitor EE-Cepheid, which is a peculiar eclipsing binary system that seems to have a dusty disk in it, not unlike the very famous star Epsilon Aurigae. Ever since then, he has been working with AAVSO data to uncover the mysteries of that strange stellar system. And today, he has come back to teach us all about it. So, ladies and gentlemen, please allow me to introduce Dariusz Kubicki.
Hello.
Mr. Kubicki? Hi, we can hear you.
Hello. Did you see my screen?
Yep, we can see your screen. Looks great.
Okay. My name is Dariusz Kubicki. I was a PhD student in astronomy at Nicholas Copernicus University in Toruń until the 1st of November of this year. The topic of my presentation is International Observational Campaign of the Eclipse of RSFA in 2020. AAVSO is an example of rare class of eclipsing binary systems where the eclipse is caused probably by a disk made of dark dust. The first discovered system of this kind is Epsilon Aurigae. For a long time, Epsilon Aurigae and AAVSO was only known systems of this kind. Here you can see images from Chara that show dark disk orbiting around Epsilon Aurigae. But the mystery of AAVSO is still unsolved. We still do not know the details of the eclipsing companion. But we have some ideas how to solve this problem. Now I will talk a little about the history of observations of EECFA. The variability of EECFA was discovered by Romano at 1956. Romano observed its minimum in 1952. Star's variability was confirmed by Weber, who reported magnitudes of the previous minimum in 1947. Basing on these two events, Romano and Perisinotto suggested that AAVSO may be an eclipsing binary. The orbital period was determined as 5.6 years. The available light curves from all 13 epochs show strong changes of the depth and the shape for particular minima. Simultaneously, variations of the colors during all eclipses remained relatively small. In 1999, Mikołajewski and Graczyk from Nicolaus Copernicus University in Toruń first suggested that the eclipse may be caused by a dark disk with a low mass star or a close binary in its center. Differences in the light curves of AAVSO may be caused by the precession of the disk. In January 2020, we announced an international observation campaign in which over 50 observers from all over the world respond to our appeal. Observations were carried out using the Johnson and Johnson-Cousins systems. During the campaign, the observers also used the photo filters in the Bayer mask in the cameras. We decided to accept such equipment because of a large number of observers equipped only with cameras. A large number of observations made by amateur astronomy enthusiasts, although burdened with large dispersion, gives excellent coverage of light curves of both the eclipse and the brightening of the star that occurred in orbital phase 0.2. We also made pioneering polarimetric observation using the Savart plates with R filter. They provided information about the change in total polarization and the light polarization angle of AAVSO. In the observations were carried out from the beginning of the eclipse over the course of a year and a half, including the brightening. We made this observation using the 90 centimeter Cassegrain telescope at Piwnice Observatory and the 60 centimeter Cassegrain telescope at Mount Suchora Observatory. This is a dome of the 90 centimeters Schmidt-Cassegrain telescope. Present in the right picture is telescope. Here you can see Mount Sophara Observatory at winter with 60 centimeters telescope at right. As I was informed, 70% of participants are amateur astronomers. So I decided to describe how to make polarimetric observations. Light curve from the star passes filter and the Savart plate and gives two images of the star. Both the filter and Savart plate must be produced for the same wavelength range. Two frames have to be made in the short period of time with two Savart plates rotated to each other by 45 degrees. It's the best to put Savart plates in automated filter wheel. We obtain two photos with doubled image of each star. Here is HFA. Then we measure flux from both images of the star. I called them F0, F19, 90, F45, and F135. This number stands for the angle of polarization. Obtained fluxes put to the first equation give the total polarization degree of the object. With the second equation, we obtain polarization angle in radians. Reduction process is the same as in normal photometry, but we have to make a flat field with air and R filter and Savart plate together. Now I will present physical properties of HFA. HFA is BE, spectral class star. E means that emission lines may be seen in the spectrum of this star. Effective temperature is about 15,000 kelvins with luminosity of 3,500 luminosities of the sun. Radius equals to 9 radii of the sun. Mass equals nearly 7 masses of the sun. Equatorial velocity is more than 300 kilometers per second. The star is strongly flattened. Equatorial radius equals to 10.6 radii of the sun, and polar radii equals 7.3 radii of the sun. Here on the picture, you can see the theoretical shape of HFA. You can also see that polar regions are much brighter than the equatorial regions. This effect is caused by gravitational darkening. This phenomenon is called von Zeipel effect. It may be observed in fast rotating stars. On this plot, you can see light curves of AAVSO eclipses from epoch -1 to 11. It's worth noting that up to 1979, observations were made using two photographic filters. First was photographic magnitude, MPG, most sensitive at blue and violet wavelengths. Today, we can compare it with B. Johnson filter. Second one, MPV, is photovisual magnitude comparable to V filter in Johnson system. On this colored plot, you can see last eclipse in 4 filters. The question is if it is similar to any previous eclipses. We found similarity between last eclipse and eclipse from epoch 3. Red points show observations from 1969 in photographic filter MPG, and the green points are observations made by AAVSO in B filter during the last campaign. Unfortunately, we cannot see any pattern between the other eclipses. Maybe the solution of this problem lies in polarimetry of HFA. On the plot, you can see that polarization degree varies from 1 to 2.2% during the eclipse and falls after the egress, especially during the brightening, there is brightening, in the 0.2 orbital phase. We can also see that polarization angle varies from 1 to 45 degrees during the eclipse, and after the eclipse does not fall down below 20 degrees. It may be assumed that the light is polarized by the disk. It is also worth noting that in order to polarize light by material from the disk, magnetic field is needed. The magnetic field may be produced by an object in the center of the disk. We made the spectral energy distribution using U, B, V, R, I, J, and H, and K filter observations, and we fitted 2 Planck curves to it. We assume start temperature as 14,300 kelvins and fit the second companion temperature this way. We found that the temperature of the companion may be about 1,600 kelvins. However, we still do not know exactly what is in the center of the disk. It may be, for example, brown dwarf, At this moment, we want to focus on the hypothesis presented in our last publication, Pienkowski et al., 2020, that the change of depth of the eclipses are caused by precession of the star. During my PhD, I tried to solve the problem by writing a program which simulates the eclipse and the product produces the light curves. Red crosses from the model and green points are observations. And in the first conception, I did not take to account von Zeipel effect. I assume that the disk is made of two disks with the gap between them. I assumed fixed opacities for each disk, independent of the angle of the inclination of the disk. I did not take into account eclipses earlier than third epoch because not enough observation points were made. As we can see, in such simplified model, fitting the first minimum was difficult to obtain. I decided to take into account the von Zeipel effect and use differential evolution procedure from SciPy Python packet. Main engine of the new program was made in C in 2009 by Cezary Gałan with my modifications. Graphical user interface and minimalizing procedure was made in Python. The program enables to fit 23 parameters, such as, for example, size of a disk, gaps, impact parameter, tangential velocity, and parameters of precession of the disk and star. At this moment, I'm reducing data that are still being sent to me after last campaign. When I finish, I will prepare a model based on conception proposed by Daniel Pienkowski in 2020. This conception takes into account the precession of the star, or both the disk and the star. At first phase, the occultation of the bottom pole is followed by the occultation of the top pole. At phase 2, only the visible top pole is eclipsed. At phase 3, both poles are being eclipsed almost simultaneously. Only at phase 4, only the visible bottom pole is eclipsed. At the end of my presentation, I wanted to thank all the observers who took part in the campaign, as their work is of great importance and will help to solve the mystery of ECFA. When I finish processing the data, the result of my work, will be published. Thank you for listening.
Thank you very much. That was interesting. Okay, so we do have a couple of questions here. So first question, when is the next eclipse coming up so people can prepare?
Next eclipse will be in 4,6, it's about 4,6 year. Because orbiting period is 5.6, but we are about 1 year after eclipse.
Okay. Thank you. Good to know. Plenty of time to get ready then. So another question, and I expect that I know the answer to this one already, but should AAVSO observers continue observing EE Cepheid, whether that is during the next eclipse or during the time leading up to the next eclipse?
Yes, I think that observations are needed since problem is not solved, but at this time, observing ECFA one time on 2 weeks is okay, is enough.
Okay. All right, just make sure it's not doing anything too unusual then, I suppose. So then that probably helps answer the next question, which we have here, which was, are observations made out of eclipse useful? Like you had shown that light curve that showed that there was a brightening. Was that unexpected? Is that something we should continue watching for?
We never see the second minima. Maybe sometime somebody could see this second minima, and it will be very helpful to solve the orbit of ECFA.
Okay, good to know. Thank you. Okay, our next question. This one's from Jose Riverio, who asks if the precession of the BE star's disk should make changes in the hydrogen alpha line.
Precession of BE star disk or precession of disk? Because BE star can have their own disk.
Mm-hmm. So I'm not quite sure which one Jose was referring to. Oh, okay, so he's clarified. He's talking about the BE star's disk. The one around the BE star itself.
I never thought about this, but maybe I should think. I should think a little bit longer about it.
Okay, sounds like a good area to explore then. Good idea, Jose.
Yes. Yes.
Okay, let's see. So I think there might be a slight misunderstanding here, but maybe you can clear it up, or for me, maybe. So we have a question asking if you have modeled the exoplanet's orbit around the binary system and whether the models match your observations. Is there an exoplanet involved here, or is the disk around a star? I don't remember.
Yes, I did models with planets like similar to Saturn or Super Saturn, but it is very not probable to occur.
Okay. Interesting. Thank you. So that brings me to a comment which I would like to share, which is that one of our webinars, I believe it was in January of this year, we had a presentation from Dr. Matthew Kenworthy, who talked about how part of his research is on planets with huge ring systems that eclipse their stars. And he did some of the similar work, like you were showing your models that involve precession. And that reminded me of some of the models that he had come up with. So I wanted to make that announcement for anyone listening. If this sounds interesting, there's another webinar which also touches on the topic. You can find that on our YouTube channel. That was Matthew Kenworthy's presentation. Okay, and looks like there's just one more question, or well, comment really, which was that the polarization setup with those subvert plates, is that how it's pronounced?
Yes, subvert plates.
Subvert plates, yes. That was very interesting. That's something that I haven't seen before for sure, and I'm glad that you shared it with us.
I describe you a very simple way to observe polarization, but as a professional astronomer, I have to make polarimetry of standard polarization, because telescope can polarize the light. So we have firstly make observation of polarimetric standards to know if our telescope or camera not polarize light.
Interesting. That makes sense. That makes sense. The same way I think we've had that talked about recently in the context of spectroscopy, how each telescope has its own spectrum that it imprints on your spectrum. So it sounds like the same thing, but for polarimetry.
Yes.
Interesting. Thank you. And we did have one more last minute question squeak in here from Jose Riverio, who had been asking about the BE stars and emission lines. Jose said that in 2014, there were hydrogen alpha emission lines, and he would like to know if you have taken any spectra during the 2020 eclipse, and are there still emission lines? Are they similar?
At this moment, I don't have any spectra made in 2020 eclipse.
Okay. All right, good to know. Sounds like we need more data during the next eclipse then.
Yes.
Okay, thank you very much. I think that's it for our Q&A. So if you could go ahead and close your screen share. I'm going to go ahead and screen share a closing slide here. Okay. Thank you. There we go. Okay, so just some quick closing announcements. First of all, I want to extend a huge thank you to both Dr. Levesque and Mr. Kubicki for sharing their time and knowledge with us today. We really appreciate it. I would also like to thank again our sponsors, DC3 Dreams and Voice Astro. DC3 Dreams provides high-end observatory automation and web-based multi-user remote imaging. The AAVSO net observatories use DC3 Dreams ACP Expert for the Bright Star monitors and other programs. The AAVSO Photometric All Sky Survey project, also known as APAS, has used ACP Expert's AI scheduler to automatically acquire over 500,000 star fields, hands-off, at a rate of 1,000 square degrees per night. This has resulted in photometry for over 128 million objects in about 99% of the sky, which is just amazing. The Boyce Research Initiative and Education Foundation provides online astronomy education, observatory resources, and research experiences to students, student teams, and schools in order to learn how to perform observations, conduct research, and publish their results in scientific journals, such as the Journal of the AAVSO. please do check out their webpage to learn more about their work. Now, I got some great news for all of us here, which is that today's webinar has been recorded. Right this very moment, you can find it on our Facebook page, and before too long, it will be uploaded to our YouTube channel, where it will join an ever-expanding library of educational videos just like this one. Now, go check it out. And if you like what you see there, please do consider subscribing to our channel. It only takes a single click, and by doing so, you will actually be helping to increase our educational reach by making YouTube more likely to suggest our videos to others. That's just one more way that you can help support the AAVSO. Speaking of support, this webinar series is being supported by you, the viewer. So if you're not a member of the AAVSO, why don't you join? AAVSO membership comes with a wide array of benefits, including access to our remote telescope network and our mentorship program, as well as our stellar photometry program, VPHOT. Seriously, VPHOT is amazing. And as always, we would be very grateful if you would consider donating to the AAVSO, whether or not you're a member. Every single donation matters and goes towards making programs like this one come to life.